Everybody, this is Mr. Walsh, and today we're going to be talking about atomic mass, or how that number on the periodic table comes to be. And when I say that number, I mean on your periodic table, the number with all the decimals. Okay, we know that this number up here is the atomic number, but here we're going to be talking about the atomic mass. Before we get into the nuts and bolts of how to figure out that value, let's look at these sorts of things. What happens if? Okay, what if? And nature can put protons, neutrons, and electrons together in a lot of different ways. I always say that they're like Legos, right? And so you put them together, and so you have three, protons, 4 neutrons, and 4 electrons, and then the next one comes along, and I have 5 protons and 3 neutrons, and so it's just a whole bunch of different Legos being joined together. And where that happens actually is in the sun. Okay, most atoms that are made in the sun. Okay, but anyways, what happens if we change the number of protons? So a proton is the atomic number. So if we go from, protons is 3, and then we change the number to protons are equal to 4, what happens to the atom? Okay, well, the thing that I am most concerned about is now we have changed the element. Okay, we've changed the element. Because remember, protons, the number of protons define the element. Okay, that was Henry Moseley in his research on atomic number and protons. Okay, so that's the first thing. Okay, what if we change the number of electrons? This we kind of probably went over when we talked about it, counting electrons. And so if you have something with a neutral charge, okay, so you have the nuclide symbol, and you go neutral, and then you change the number of electrons, so now you have a -1, or maybe you have a +1 charge. Okay, changing the number of electrons means that you've made what we call an ion. Okay, and there's a positively charged ion, which is called a cation. There's a negatively charged ion, which is called an anion. Okay, so there's the different ions. Okay, but if we change the number of neutrons now, okay, if we go from 32 neutrons to 33 neutrons, okay, that doesn't change the element. It doesn't make it an ion because there's no charge. What that does is it changes the mass. Okay, and when it changes the mass, this is something called an isotope, which are isotopes are the same element. They may be ions, maybe not, but isotopes have the same number of protons with different numbers of neutrons. Isotopes. Okay, so this is what we're going to talk about when we talk about atomic mass. So an isotope here is what I just said it was. Okay, and then keep in mind that nature puts isotopes together. Well, maybe if it helps if you can see it here. Nature puts together isotopes in a lot of different ways. Okay, and so there may be elements that have 2 isotopes. Okay, but the heavier the element, meaning the higher the atomic number, the more protons, the more likely it is that you're going to have more combinations of neutrons that work that are stable. Okay, and so while I'm not going to show you the simulation in the middle of this video, you can definitely go to it. I'll put the link in the description. But the simulation will show that something like let's see, carbon has, like 2 naturally occurring isotopes, okay? And something like fluorine has 1 naturally occurring isotope, and neon will have 2 naturally occurring isotopes, because if you have too few neutrons, again, Legos, so if you have too few neutrons in your structure, you're going to have something that is unstable. And then if you have something with too many neutrons, okay, you're going to have something that is unstable. So there is this band of stability where you may have 1 or 2 isotopes that occur naturally, or if you have elements with a ton of protons, it's possible to have 10 or 12 isotopes that naturally occur because you have a bigger nucleus that can be more stable with bigger changes in the number of neutrons. Okay, so let's move on from here and let's talk about atomic mass. Atomic mass is the number found on the periodic table. Okay, and so atomic mass is this number on the periodic table. We have the atomic number, but the other number on most periodic tables is the atomic mass. So it's the one that's reported out to a ton of decimals. Okay, and the way that we get the atomic mass is using a process called mass spectroscopy, which is going to give us not only every isotope, it gives us each isotope and its mass number, okay, but it also gives us the abundance of each isotope. Okay, it tells us how much of each isotope is there. Okay, and we get that in a percentage. Okay, so mass spectroscopy, I'm not going to explain what it is, but it's a process. We can't do it here. It's way expensive, millions of dollars to buy a mass spectrometer. There's some that are cheap, but you don't want to use cheap ones. Here's how you do this. Okay, you're going to calculate the atomic mass by taking the abundance, so this is the percentage, and you're going to multiply it by the mass. Okay, and the mass, in this case, that's the mass number of each isotope. So from the mass spec, we can see that bromine has 2 naturally occurring isotopes. Okay, and so this is how we're going to do this. We're going to take the abundance, okay, so of this one is 50.69, and whenever we do math with a percentage, okay, whether it's in chemistry or math or out in the real world, what we do is we never use the percentage, but we always move the decimal over 2 spots. Okay, so move the decimal. I'll put that here. Move the decimal 2 places. Okay, so you want to move the decimal 2 places for the percentage. Okay, and then we're going to multiply that by the mass number, which is here. So we're going to take this and multiply it by this. Okay, we're going to do the same thing here. Okay, the abundance, 49.31, but move the decimal 2 places, so we get 0.4931 times the mass. Okay, we break out our calculator. Okay, and so let's make sure that you can see it. Okay, so we'll do 0.5069 times 79, and we get 43.50451. Don't use significant figures, okay? We're not going to do that for mass, okay? We're just going to report the number based on the calculus. Don't round, don't do anything. And then the next one is 0.4931 times 81. And we do 39.9411. We're going to add those numbers up. So plus 43.504. 0.50451. I think I made a mistake. Let's go back. 0.5069 times 79. Right. This number is incorrect. See, it's possible to make mistakes. I make mistakes. Everybody makes mistakes. Okay, so 4051 plus 39.9411. And so we get 79.9862. And the units on that number are AMU, atomic mass units. So how do I know that this is correct? Here's what I'm going to do. I'm going to pull out my periodic table, and I'm going to look at this mass and compare it to bromine here, and I see that the mass in the periodic table says 79.904. Okay? These two are close. The reason why they're close and not exact is because we rounded some of these numbers here. Okay? We didn't round our answers, but like this is rounded and this is rounded. So we want to, so even when it's rounded, we get an answer that is slightly off from the actual answer. And so just to let you know, this is what the bromine mass spec looks like. Okay, so we'll do this. So look, each of these things, this is called a peak. So we have a peak at 79, we have a peak at 81, and so it gives us the mass number. Okay, here the x-axis is mass number. Okay, and then up here, this is the percent abundance. And this I found right on the internet. Okay, so it gives you the two things that you need in order to do this problem. Okay, you take the mass number times the percent. Again, move the decimal over two places. Okay, you multiply those two numbers, take this number, multiply it. Okay, and then you take those two answers and you add them up and you get your overall answer. That's why I like mass spec. It's a very technical tool. There's a lot of things that go into how mass spec works, but ultimately it gives you the answer of what we have on the periodic table. Let's ask the question, looking at this, okay, how many isotopes are on this mass spec? Okay, there are, in this case, 2 naturally occurring isotopes. If we look just at the peaks, there is this one here that's pretty obvious. So we have carbon 12, okay? But look, up here when we look at the percentages, there are 2 percentages, and then if you look down here, right down here, okay, you'll see this little itty bitty peak right here at carbon, okay, carbon 13, okay? So this is 98.93% abundant. This is 1.07% abundant, okay? Then once we get this number, then we can take these and we can do the math and we can figure out the atomic mass, okay? Again, all just from the mass spec, okay? So it says, now we're going to do some math sense, okay? It says, is the atomic mass going to be closer to 12 or 13 after you do the math? So without doing the math, let's see, we have 2 peaks on this thing, okay? And we do the math on the 2 peaks, but what would you think? Do you think that the mass is going to be closer to 12, or do you think the mass is going to be closer to 13? Which peak is bigger? Okay, the peak of 12 is much, much bigger, so because it's much, much bigger, we're going to be closer to the atomic mass of 12 AMU. Okay, the bigger the peak, the closer the number is to that mass number. Okay, the natural. So when we do the math, it's going to fall way closer to 12, and we can actually verify this. If we look at the actual mass on the periodic table, carbon is 12.011 AMU, and that's what we see. This is 12.011. It's much, much closer to 12 because this peak is much, much bigger. How many isotopes does silicon here have? And this one's a little easier to see. We have 3 peaks that are pretty obvious. So we have silicon that is 28. Remember, this corner is the mass number. Silicon, which is mass number of 29. and silicon, which is mass number of 30. Okay, so we have 3 isotopes. Okay, it says, what is the most abundant isotope? Well, the most abundant isotope is 28. And so if that's the most abundant isotope, that means the mass, after you do the calculation, is going to be closest to 28. That's trying to, what the point is you're trying to get a number sense of what your answer is going to be so that it makes sense when you figure out, when you actually get the answer, you can go back and check after you calculate it. So it's going to be closest to 28 here, okay? But let's go ahead and calculate it, okay? Because now we have 3 peaks. So let's do that. So we're going to do silicon 28 is 92.23% abundant. Silicon 29 is 4.68% abundant. And silicon 30 is 3.09% abundant. Okay, so now remember, we have to move 2 places to do the math with the percentage, so we're going to move this 2 places. Now, here, even though it's a single digit percentage, we still have to move it 2 places, so it's going to be 0.0468. Okay, same thing here, we're going to move it over 2 places. Okay, so it's 0.0309. And then we're going to multiply 28 times this, 29 times this, 30 times this. Let's make sure I do the math correctly here. You guys can double check my math. Okay, so we do 28 times 0.9223, and that's going to be equal to 25 point. I know that you guys may have a straight on view for this, but for me it's on an angle, so it's hard to see. So this is, let me see, 25.8244. Then we're going to do 29 times 0.0468. Okay, so this is 1.3572. Okay, so again, remember we moved the decimal point over 2 places. That's why we had 0.04. Okay, and now the next one is 30 times 0.0309. We do that and we get 0.927. Okay, so now we're going to take all of these and we're going to add them up. So we get 25.8244 plus 1.3572 plus 0.927. And we get 28.1743 AMU. And we can verify this 2 ways. First of all, 28, that's what we were expecting, a number very close to 28. Okay? The second thing is we can go to the periodic table and we can look at silicon. Silicon is here, 28.0 on the periodic table, 28.086 AMU. And again, the reason why they're different is because we did some rounding here to make our numbers work out a little easier for us. Okay. Now the other thing is if we didn't know it was silicon, okay, maybe we didn't know. So what you can do is you can calculate the mass, the atomic mass, and then go to the periodic table and find a mass that's close to 28. And you will see that silicon is 28, aluminum's 27, phosphorus is 31, and so the only possible choice that this could be is silicon. Okay, there's not any other element with that. There's very few elements that have very close atomic masses on the periodic table. Okay, so there you have it. That's how to calculate atomic mass using mass spec data. Have a great day, everybody.